We covered probability in general in the first part of chapter 13, and in 13.4 we're going to look at what we call compound probability. And that compound part of that, a compound event is an event that's made up of two or more events occurring together. So we can find the probability of compound events by using the probability of each part of that compound event. And there's different types of compound events also. If the occurrence of an event does not affect how another event occurs, we call those independent events, so that means they don't affect each other. If they do affect each other, so the occurrence of an effect does affect how the other one occurs, we call those dependent events. So just separating those two situations, if they don't affect each other, that's independent. If they do affect each other, that would be dependent events. So if we're going to calculate the probability of a compound event, we first have to decide what type it is, if it's independent or dependent. So a quick example, if we're traveling from Orange County, California to Chicago, we got to ask if the probability of rain in Orange County will affect the probability of rain in Chicago. Answer to that would be no. They're so far apart that if it's raining in one city, it's not really going to affect the rain in the other city. So since they don't affect each other, that would be an example of events that are independent. So a few more examples to look at and decide if they're dependent or independent are, for example, if we choose a number tile from 12 tiles and then spin a spinner, those are our two separate events, choosing that number tile and spinning a spinner. That would be an example of compound event that's independent, because whatever I chose on the tile is not going to affect how I spin that spinner. So the results from one event is not going to affect the results of the other. So second type, if I pick one card from a set of 15 sequentially numbered cards, and then without replacing the card, pick another card. This would be an example that is dependent, and it's an important piece in there that makes that dependent, and that's because I didn't replace that first card. So say, for example, if I chose a number 10 from that first choice, so if I chose the card number 10, if I want to pick another card that's, say, for example, even, depends on the first card that I chose. So since that second card is affected by the first one, that would be an example of a dependent event. So last situation, if I roll a number cube and then flip a coin, that's another example of independent events. Doesn't matter which number I roll, it's not going to affect that coin flip. So since those are two events that happen separately, that would be another example that's independent. So in that first case, if I have two independent events and I find a probability of them both occurring, so event A and event B, if I, again, know that they're independent, then I can take those two probabilities separately and just multiply those together. So take the probability of my first event, multiply that by the probability of the second event happening. And we'll see an example of that next. So again, if I think of independent events, if I start with a desk drawer that contains 5 red pens, 6 blue pens, 24 silver paper clips, and 16 white paper clips. If I want to pick a pen and a paper clip from the drawer without looking, I got to find the probability that I select a blue pen and a white paper clip. So first of all, we're told that they're independent events, but if I think about that for a second, they're independent because whatever pen I chose shouldn't really affect what kind of paper clip I chose. I'm choosing one type of each item, but it doesn't matter which item I chose first. I'm still making a separate choice for my second paper clip. So if I want to find the probability of that first event, selecting a blue pen, I have 6 blue pens and I have 11 pens total. So that would be 6 out of 11. Probability of a white paper clip, same idea. I have 16 white paper clips. I have 40 paper clips in total, so that would be 16 out of 40. And if I want to find the probability of both independent events occurring together, so probability of selecting that blue pen and a white paper clip, I take those same two probabilities and I multiply them. So 6 over 11 times 16 over 40. As a decimal, that comes out to about 0.218. So we can just answer that as a decimal. We can answer as a fraction, or also put the percent there. 21.8% would also work as an answer. So that's an example. Again, if I have two separate probabilities and they're independent events, I just multiply those probabilities together, and that gets me a combined total. So next type, same question. We roll a standard number cube and spin the spinner shown. We want the probability that I roll a number less than 4 and the spinner lands on a vowel. So again, if they're independent events, and they should be because whatever number I roll shouldn't affect how I spin the spinner, so those are independent, I take the two probabilities and I find them, multiply them together. So the first probability, probability of rolling a number less than 3, that should be, read that as less than 4, but that should be less than 3. So I should change that to a 2 over 6, probability that I roll a number less than 3 instead of 4, because that would be either a 1 or a 2 that I could roll out of the 6 on that number cube. And if I want the spinner to land on a vowel, that would be one vowel out of the 4 letters that are there. So that would be a 1 in 4 chance of spinning a vowel. So if I take those two probabilities and multiply them together, and again that first one should be a 2 out of 6 because there's 2 numbers less than 3. If I multiply that times the 1 in 4 chance that we get the spinner correctly, that's 2 over 6 times 1 over 4, and I could reduce that to 1 out of 12 instead of the answer that I had written there, not 1 out of 8. That would be the chance of getting both. So again, the probability of rolling a number less than 3, that's 2 out of 6. Probability of getting a vowel, that's 1 out of 4. If I multiply 2 6 times 1/4, that should reduce to 1/12. Towards the bottom of the page, we have another type of event to describe. So events that can't happen at the same time, we call those mutually exclusive events. So think of raining in this case. It can either rain or it's not going to rain. It can't be both at the same time. That would be an example of something that's mutually exclusive. So if A and B are mutually exclusive, again, that first part's saying the probability of both happening at the same time is 0 because they can't have any probabilities in common. But if I want to find the probability of either the first or the second event happening, I can just take those two probabilities and add them together. So we're going to see that on the back in this first example. Student athletes at a local high school may participate in only one sport each season. And that's the part of this question that makes it mutually exclusive. I can't contribute to both sports at once. It's got to be one or the other. So during the fall season, if 28% of student athletes play basketball and 24% are on the swim team, we want to use that to find the probability that a randomly selected student is going to do either or. They're going to play basketball or they're on the swim team. Again, can't be both because we're told that it can only be one sport each season. So if they are mutually exclusive, can't be both at the same time, find the probability of a basketball or swim team is your randomly selected student, is I can take those two probabilities and add them together. So again, the probability of them being in basketball, I could say that's 0.28. Probability of being on the swim team was 0.24. So if I take those probabilities and add them, I should get 0.52. Again, we can answer that as a decimal, fraction, percent, doesn't matter. I just left that as a decimal. Same type of question is next. We're again told that I can only be in one sport at a time. So if 15% of athletes play baseball and 23% are on the track team, if I want to find the probability of an athlete either playing baseball or on the track team, that'd be another example of mutually exclusive events that I can add together. So 0.15 plus 0.23 for my two probabilities. Add those together, I get 0.38, or you could also answer 38%. That would be your combined probability because those are mutually exclusive. And if events aren't mutually exclusive, they could have outcomes in common. We call those overlapping events. So our last examples didn't have any overlap because I can only do one sport each season. But if I could play more than one sport, that could be an example where students are playing both at the same time. So another example, in a standard number cube, if I find the event of rolling an even number or the event of rolling a 3, that has an overlap because if I roll 6, that's both even and it's a multiple of 3. So it's a favorable outcome for both types of events that were described. So if I do want to find the probability of overlapping events, it's the same idea as when they're mutually exclusive. Probability of A or B is going to be adding the two separate probabilities, except in this case, I have to subtract any area that they overlap. So I have to subtract the probability that it's both occurring at the same time, A and B. And in our example for this, we have the probability of rolling either an even number or a multiple of 3 when we have the standard number cube, and we had that example up above also. So if I want to find that probability where it's even or a multiple of 3, again, since there should be some overlapping events there, I can add the two events separately and then subtract the probability of them overlapping. So probability of rolling an even number, I should have 3 even numbers out of the 6 on that number cube. If I'm looking for multiples of 3, 3 and 6 are both multiples of 3 on the number cube, so that's 2 options out of the 6 still. And the probability of it being both, even and a multiple of 3, if I roll a 6, that would be both. So that would be one option from those 6 on your number cube. So again, adding the chances that it's even plus the chances that it's a multiple of 3, but also subtracting the overlap, I should end up with 4 out of 6. And that you could either leave as an answer or you could reduce it, but that's what we're looking for. We're adding the two probabilities together, but subtracting any overlap they might have. So same situation on the last one. I want to find the probability of rolling an odd number or a number less than 4 if I'm rolling that number cube. And again, this should be an example where there's some overlap. An odd number, there should be 3 odd numbers, 1, 3, and 5. So 3 numbers out of 6 I can get as odds. Numbers less than 4, that's either 1, 2, or 3, so that's another 3 numbers out of the 6 that are less than 4. But again, since they overlap, odd numbers that are also less than 4, that would be 1 and 3. So if I roll either a 1 or a 3, that would fit under both categories. That's what's counting as overlapping. So if I take away those two options, if I roll a 1 or a 3, that's both odd and it's less than 4, that would complete my overlapping equation. So first event, odd numbers are 3 out of 6. Numbers less than 4 are also 3 out of 6. But since 1 and 3 are both overlapping, I have to take those away, and that should result in another 4 out of 6 probability of getting that. So just got to decide if they're overlapping or mutually exclusive. That'll decide if you have some overlap to subtract. Make sure you have these questions complete. See if you can answer the video questions for these also, and come into class prepared to do some work.